Hello, welcome to using the rational root theorem to solve polynomial equation. And polynomial equations look sort of like this. Well, polynomial equation equals 0 and has rational coefficients, including a rational constant term. It can be solved using the rational root theorem if there are no more than a total of 2 irrational and complex solutions. Now, we would want our coefficients to be integers to use the theorem. But if they're rational numbers, we can multiply through as a preliminary step to by the least common denominator to obtain integers. So this is the form we're looking at. We can have missing terms, that is allowed. The rational root theorem of the tells us that the roots of the equation are of the form P over Q, where P is a factor of the constant term. The constant term is the factor for the numerator, and Q is the factor of the lead term, which is, gives us a factor of the denominator. We look at 5x and 6, and there's little terms in here, and plus 3. And we ask what are our candidates for our rational roots. It would be a factor of 3, which is 3, 1, -3, or -1. So look at these numerators, 3, 1, -3, -1, divided by a factor of the 5, which is 5, 1. And if I put the -5 and the -1 in, I would end up duplicating solutions. For example, I get a negative over negative instead of a positive over a positive, and it's not worth doing that. So I have 8 distinct candidates. The highest degree of the variable determines the number of solutions a polynomial equation has, but they're not necessarily unique. The technique is to evaluate the polynomial for the candidates in a list that we have made. And when they produce a 0, we would find the factor. So if I get a solution x equals 1, I subtract 1 from x and get a factor, and divide the factor out of a polynomial, reducing its degree by 1. And I would repeat this until I get it down to either a quadratic or linear equation that I can handle. As an example, 2x cubed plus 5x squared minus 2x minus 5 equals 0. There's a 0 on the right. We need to make sure of that. And there are 3 expected solutions. Our coefficients are integers. Our constant is an integer. The candidate list comes from the 5. 5 over 1, 5 over candidate to put in the denominator. So 5 over 1, 5 over 2, 1 over 2, 1 over 1, and the negative versions. We have, in this case, 8 candidates. We'll try things from our list. I like to start with simple numbers like 1 and hope I get lucky. Might as well, because it's got as much chance of working as anything else. So I plug the 1 in. 2 times 1 cubed plus 5 times 1 squared minus 2 times 1 minus 5. And that does equal 0. So 1 is a solution of the polynomial, and x minus 1 is a factor. So I would divide x minus 1 into the polynomial, and I would end up with 2x squared plus 7x plus 5. So I got x minus 1 times 2x squared plus 7x plus 5 equals 0, which I can factor as a quadratic. And if I don't see the factors, I could use the quadratic formula. So now I have all three of my solutions, x equals 1, -1, and -5 pairs. To find the polynomial a degree lower, I could actually use long division, which at this stage I would assume most people would be familiar with the process. This is worked out step by step. If you're not, I would take a screenshot and print it and go over it. So we have three factors, and we have a very powerful rule in algebra. And if we have a product, in this case, three participants in that product, that's equal to 0, this can only happen if one of these factors equals 0. So we would set these three factors equal 0 and get our three solutions. And here they are. If the polynomial still does not become a product of linear factors in a quadratic term, I'll find and remove another root until either factoring or the quadratic formula can finish find all of the zeros. And I'm going to caution you, it may not happen. If you have too many complex numbers or too many irrational numbers, you're not going to find them. If a root is repeated n times, it is said to have multiplicity n. So, and that would count as n different roots. See what we mean by that? We take something very simple that we can even factor. X squared minus 2x plus 1 equals 0. This is x minus 1 times x minus 1, which gives me x equals 1 multiplicity 2, because I get it from this factor and I get it from this factor. And that would count as the two roots I need. It is possible to have a clue as to how many positive roots and how many negative roots a polynomial equation has. And this is important because when we find all of the possible positive roots, we don't need to try other positive values from our lists. So we just insert any random positive value into the polynomial and count the number of sign changes. This is the most possible positive real solutions. And if we do the same with the negative number, the negative sign changes, now the sign changes caused by plugging in a negative number will give me the most negative solutions. And we have to subtract 2. So if I come up with 4 possible positive roots, I have 4, 2, or 0. So determine the possible number of positive and negative solutions of the equation found x to the 5th plus 3x to the 4th minus 2x cubed minus 6x squared minus x minus 3 equals 0. I'll plug a positive number in. I like 1. 1 to the 5th is positive. 3 times 1 to the 4th is positive. Negative 2 times 1 cubed is negative. Negative 6, 1 squared is negative. Negative 1 times 1 is negative, and negative 3 is negative. I have one sign change right here. So I only have one positive solution. Substitute the negative value in, negative 1 to the 5th, that's negative. 3 times negative 1 to the 4th, positive. Minus 2 times negative 1 cubed, that's a positive. Negative 6 times negative 1 squared is negative, and negative times the negative 1 is positive, and of course negative 3 is negative. 1 sign change, 2 sign changes, 3, 4. So I have 4, 2, or 0 negative solutions. But we got to be careful. These are real solutions, not necessarily rational solutions. So I might have the square root of 5 as a positive real solution, and I might have the negative square root of 5 as a negative as a negative solution. But it's a good idea to do this because if we exhaust all of our positive or negative solutions, we can cut the candidate list down considerably. Okay, what happens if not all the powers of the variable occur? The rule is the same. Count the sign changes and ignoring missing terms. X to the 4th minus 2x squared plus 1. We'll use that as our example. I'll put a positive number in, 1, positive, negative, positive. So I got 2 or 0 positive solutions. If I put the negative in, I would have found the negative solutions. Find all the solutions for x is 6 plus 3x to the 4th minus 4x squared equals 0. Well, here we have a problem. We don't have a constant term. But if we factor out x squared, we get x to the 4th plus 3x squared plus 4 equals 0. This is going to give me 0 as a solution of multiplicity 2, and I can work with this polynomial in the rational root theorem. So the remaining solutions, or I'll take the 4 and the 1, and so I have 4 over 1. Another factor of 4 is 2, 2 over 1. The other one is 1, 1 over 1, and the negatives. So I end up with 6 candidates. This one is nice. They're all integers. I can see plugging a positive number in that I have one sign change, so I got at most one positive solution. Put the negative value in. I have one sign change, so I got at most one negative solution. So we'll try 1, and then we're going to find out that 1 is indeed a solution. There's no need to try the other 2 positive candidates. I'll try negative 1, and I will find it is also a solution, so there's no need to try the other 2 negative candidates. So I now know that I have x squared, x minus 1, x plus 1, and after I divide these out, I would find I have x squared plus 5 equals 0. So I have to solve x squared plus 5. Solving that, I get x squared is negative 5. Well, x is plus or minus the square root of 5i. My other 2 solutions. So I have 6 solutions. 0 multiplied multiplicity 2 plus and minus 1 and plus and minus the square root of I. And this is how I would express that.